Let's talk about the most important part of a plant, the part you never even see, the root system, right? It's this whole hidden world beneath the surface. Today, we're not digging in the dirt. We are diving straight into the code that builds a digital version of this secret world. And it is fascinating.
So here's the game plan. We'll start with why this is such a tricky problem to begin with. Then, we'll peek at the blueprint for a single root, kind of like its digital DNA. From there, we'll see how the whole system gets built, bring it to life with some rules, and then, the important part, teach it how to eat. And finally, we'll wrap up with why this is such a game changer. Ready? Let's get into it.
All right, so first up, the big challenge. We're trying to model something that's completely invisible. I mean, the roots basically run the show when it comes to a plant's health. But for growers, for scientists, they're a total black box. How do you optimize something you can't even look at?
I mean, that's really the core question, isn't it? You can't just, yank a plant out of the soil every morning to see how the roots are doing. That's a surefire way to have a very dead plant. So if we can't look at them directly, what's the solution?
Well, you build its digital twin, a simulation that's so detailed it grows, it behaves, and it reacts just like the real thing. And that is exactly what we're going to do in this explainer. We're going to walk through the code and see how you build a living, breathing virtual plant right from the ground up.
Okay, so just like any building project, you've got to start with a blueprint. Our digital plant is no different. It's all built from these fundamental little pieces, its digital DNA, that are all laid out right in the code.
First thing you have to know is the model is smart enough to know that not all roots are created equal. It breaks them down into three main types. You've got your find roots. These are the super thin, hard-working ones doing all the heavy lifting of nutrient absorption. Then you have medium roots, kind of a mix of absorption and transport. And finally, your coarse roots. Think of these as the big structural highways that hold the whole plant in place.
Now, trying to simulate every single microscopic root hair would be, well, computationally insane. So the model does something really clever. It uses this concept called a root cohort. It just groups roots that are basically the same age, same type, same size, into one batch. This right here, this is the fundamental Lego brick we're going to use to build the entire system.
And every single one of these Lego bricks has its own stat sheet. The code is tracking everything: its age in days, its total length, its diameter, how much it weighs, and this one is absolutely key, the activity factor. It's just a simple score from 0 to 1 that tells us at a glance how healthy and efficient that group of roots is right now.
Okay, so we've got our bricks, our root cohorts. Now it's time for the fun part, putting them all together. We're moving from just having the pieces to building a whole complex architecture that actually looks and acts like a real root system. To do that, the model slices the world up into these root zone layers. Just picture taking the pot the plant is in and cutting it into a stack of horizontal discs. Each disc, each layer, has its own environment, its own temperature, its own oxygen, its own food, and the model knows which root cohorts are growing inside each one. This spatial organization is so important. And the model's adaptable too. It knows that roots grow totally differently depending on where they are. Take an NFT system, for example, where roots are just in a thin little film of water. Their growth is pretty restricted. But in deep water culture, they're submerged with way more freedom to branch out. The code actually has built-in multipliers to adjust for all of this automatically.
And you can really see that difference right here. NFT is our baseline, we'll call it 1.0. DWC gives the roots a little more freedom, so it gets a 20% boost. But then look at Aeroponics. The roots are just hanging in the air, they can go wherever they want. So the model gives it a branching multiplier of 3.0. That's a huge difference in how the root architecture develops.
So we've built the structure. We've got our layers, we've got our cohorts, and they're all arranged based on the growing system. But right now, it's just a statue. It's a static model. The next crucial step is to breathe life into it. We need to program in the biological rules that tell these digital roots how to grow, how to compete, and, eventually, how to die.
So, how does a digital root decide where it's going to grow? Well, it's not really thinking. It's just following a set of 5 core rules. 1. Follow the hormones, like auxin, which are strongest up near the base of the plant. 2. Find the food. It's always going to push towards zones with more nutrients. 3. It has to breathe, so it seeks out oxygen. 4. It doesn't like crowds, so growth slows down in areas that are already packed with other roots. And 5, it's a bit of a princess. It likes the temperature to be just right. Of course, just like in real life, these digital roots don't live forever. With every daily update in the model, they get a day older. And as they age, that health score, that activity factor, starts to decay. Those little fine roots that do all the work, they burn out the fastest. The big, coarse structural roots, they're built to last. And every single day, each and every cohort has to roll the dice. It faces a probability of dying based on its turnover rate. It's digital natural selection.
All right, we've built a root system and we've brought it to life. Now, let's get to its entire purpose for existing: to eat. The whole point of this incredibly complex architecture is to pull nutrients out of the environment. So let's see how the simulation actually calculates this.
Okay, to make this super clear, let's just set a baseline. Let's say under absolutely perfect, ideal conditions, our root system has the potential to absorb 100 units of nutrients. That's our starting point. Now, let's start messing with the environment.
First, change the water temperature creeps up a bit, from a perfect 20 degrees Celsius to a warmer 24 degrees. This should speed up the root's metabolism. So, what does the model predict will happen to our uptake?
Boom! It jumps all the way to 126. See, the code uses a biological rule of thumb called the Q10 factor. It basically says that for every 10-degree rise in temperature, a lot of metabolic processes speed way up. In this case, that little bit of warmth actually made the roots better at their job, more efficient.
But okay, let's throw another wrench in the works. The temperature is still nice and warm, but now the pH of the nutrient solution drops from a happy 6.0 down to 5.0. That's starting to get too acidic for the plant to easily absorb a lot of key nutrients.
And there it is. The potential drops from 126 back down to 118. Even though the temperature is great, the bad pH created a bottleneck and the root's efficiency went down. And this right here is what makes the model so powerful. It can stack all these different environmental effects on top of each other to give you a really realistic picture of plant health. So we've gone from a single concept in the code all the way to a living, eating digital root system, and that's really cool. But what's the actual point? Why does this matter? Let's connect the dots from this abstract simulation back to the real world of growing actual food.
This is why. This is the payoff. The model spits out this incredible dashboard of vital signs that are otherwise impossible to get. A grower can see the total root length, the total surface area for absorption, the overall health factor, and the exact amount of nutrients being taken up every single day. It's like giving your plants an MRI. You get this unprecedented deep insight into that hidden half.
And that brings us to a really mind-bending final question. If you can use a model like this to run thousands of virtual experiments, testing every possible environment, every nutrient recipe, every genetic trait, you can find the absolute perfect root architecture. So the question stops being, how do we grow this crop, and starts becoming, how do we design this crop? If we can digitally perfect the root, are we getting close to designing the perfect plant?